everyone. All right, there are plenty of questions about quantum computing these days, and our panel has all of the answers, which means we're going to put some hours back in your day. I want to introduce our panelists. Sitting immediately to my left is Karl Dukatz. Did I pronounce that right?
That's right. Yeah.
Yes. Who is a managing director at Accenture and one of the main people in their quantum computing practice. Next to him, Olivier Ezratty. How'd I do?
Yep, that's fine.
Fantastic. The co-founder of the Quantum Energy Initiative, and then farthest over, my colleague Will Oliver, who is a professor here at MIT and the director of the Center for Quantum Engineering, and co-author, along with me and Jonathan, of the first article about quantum computing to appear in, and I think so far the only, to appear in Harvard Business Review. Will's job was to make sure Jonathan and I, and the editors at HBR, did not say anything that was wrong, and he had by far the hardest job on that article. I want to start off just by giving each of our panelists the floor for on the order of 5 minutes to tell the room what they need to know about quantum computing, the state of it, where we are today, separate signal from noise. Take your time and do what you want with it. I also want to let everybody here know that we're going to reserve some time at the end for questions from the audience. So please, as we're talking, think about what's top of mind for you, and when it comes time for Q&A, don't be shy. This is a fantastic opportunity to ask some folk who are in the know. Karl, can we start with you?
Absolutely. So a little bit of background about myself. I've been in the quantum ecosystem now for roughly 10 years. We started our program at Accenture in around 2016. And
what did you see in 2016 that led you, because that was fairly early. Why did Accenture decide to get into quantum that long ago?
Yeah, we closely monitor startup ecosystems, and at the time, there was a slew of startups that were coming out that were offering capabilities, algorithmic capabilities that were translating different nuances and workflows into platforms. And so they were trying to take this is around the time variational algorithms were coming available, and so they were looking at these new variational algorithms. So before that, we just had Shors and Grovers and some of the foundationals, but now there were new ways of using quantum computers. They were exploring optimization and machine learning and chemistry with these new algorithms and said, hey, let's start some businesses and see if we can get momentum in getting people to use the rudimentary devices that were available at the time. A lot of it was optimization on D-Wave, but at the time IBM was coming out with some of their earlier processors, and we knew that there was other people working on building machines. There were some Rigetti devices, we were monitoring ion traps, but by looking at the ecosystem, determining that there was a software layer that was interesting for our company where we like to work, where it's enablement, access, training, and development for people using systems, and then that allows access to businesses to then utilize them for purposes that they need. We decided to engage. Really, that's what got us started, and it was a lot of fun to go through the learning process that I think Neil was kind of mentioning as well. Is how are these systems useful? What can they do? What are the extents? Given a particular chip and its topography at the time, what type of problem could you embed on it? What type of algorithm could you run? How would that compare to classical? Looking at the spectrum of different types of devices that were available, so it wasn't just the quantum computers or the QPUs, but then there were also simulators for quantum computers that you could measure against, or digital versions, digital annealers, or digital representations of quantum computers built in FPGAs or other ASIC circuitry that were trying to compete and give speed up and show what could be done. There's a vast array of different systems to play with and learn about. And so that's really where we started, is getting into that. And then we developed a program that's called Quantum Business Experiments. And what this was about was taking any type of business problem, analyzing the data that you use for it, the type of algorithm that's run, and the optionality of using a quantum algorithm for solving that particular problem. And then projecting out, okay, here's the best-in-class version of a classical algorithm to solve the problem. Here's what we can do with a quantum computer today. what's the gap between, can we distill the problem down to something that can actually run on quantum hardware, and then as quantum hardware gets better, you can add features back into it so that you have a functioning quantum application as soon as the hardware is ready. That's kind of the theory.
Yep.
And so we've been working on that over time with many different organizations. There's hundreds now of different applications that we've built with that in mind, with this comparative analysis as the kind of the thought behind it. And we've launched some different programs with the World Economic Forum now, where there's a quantum applications hub where you can go see and experience a bunch of these runtimes. And then we work closely with the Quantum Economic Development Consortium as well. I lead the use cases TAC with a technical advisory committee within the QEDC, and we use that as a platform to bring businesses and quantum computing companies together in large workshops where we'll ideate hundreds and hundreds of different areas where quantum computers can be used, and then distill down which ones the industry should start with. We've done this in financial services and pharmaceuticals and energy, and those reports are useful across different swaths of enterprise to get started essentially in this field. And so, I think when I look at the evolution of where we've been, when we started, everyone asked, what is quantum computing? And now most businesses have someone who understands what quantum computing is. And when we talk to them, they say, how are you going to advance my program? How are you going to take this to the next level? They're no longer asking the fundamental questions of what is this and why do I need it? But they're seeking to get scientific or other insight that will help accelerate them into this ecosystem in a more efficient and effective manner.
And what have you learned in 9 years? Is the landscape more clear or more kind of difficult to see? Has your crystal ball about quantum gotten clearer or cloudier in 9 years?
I would say that it is definitely clearer, and thanks to some of the work that we've been doing with Neil as well to build these calculators to understand all of the dynamics of the features of the systems and the chips and the algorithms and the current state of classical. Like when all that comes together and you have a view of it, it's really helpful. But I would say the other thing too is understanding when there are things that are there's hype, there's things that are very successful in the industry, and then you kind of have to be patient and wait them out. Let the process of business and science happen, and then you kind of reshift your thinking based on what's changed. We've seen some devices come out with large amounts of promise, and then slowly, their usefulness is whittled down to a specific selection. And we're like, okay, we thought all of this, but now we know this, and so we'll use it in that capacity. But we have to look for now something that fills this other gap. And you see this, it showed earlier the different modalities of qubits, and understanding which modality of qubit you use for which business problem because of the type of processing or speed up that you need or the efficiencies you're trying to gain is an important mapping. And that bounces around all the time. When we started this, we thought optimization was the spot with the new algorithms that were variational. We thought, this will be great. It's ubiquitously, it applies across all industry. Everyone needs optimization. But then you get some operations researchers in the room, and they say, well, this is how we solve the problem. This is why we do it. And your quantum computer doesn't really plug into our process anywhere. So, we've been doing this research for hundreds of years. Show us the way, and it takes a lot to convince and to move that ecosystem forward. So we pivoted, and we said, okay, maybe machine learning is the next one. Or now we're on to chemistry as the area, because it's the most direct comparison of a way the quantum computer works to the physics problems that we're trying to solve. And it's still like following this pathway and journey and going through the process of thinking about each of these spaces and then isolating what works and what doesn't. That's why I say there's more clarity in the ecosystem at large than I think there was when we started.
Olivier, what do we need to know as we start our quantum technology day here?
What do we need to know about anything?
Sticking to the agenda for the day would be helpful, I think.
Yeah. there's a lot of things to understand. First, I should introduce myself a little bit. I'm a software engineer by training. I spent about 20 years of my life in the software industry, and then I became freelance, superposed the state kind of independent guy, teaching, writing, podcasting, consulting, advising many organizations. And I discovered the quantum field about 8 years ago. But my first bump on that was similar to yours is when Google and D-Wave announced that they had crafted a solution which was 100 million times faster than a PC. I was interested. I was willing to understand what the heck is that. And what was funny is that when I looked at the papers which were describing what it was doing, I knew that anybody who was writing about it didn't understand what they were writing about, because it's so complicated to understand quantum annealing. Nobody knows about it, at least back then, 10 years ago. So then 8 years ago, I started to study that. And I'm defining myself as a kind of continuous learner. I'm a student, but I'm teaching. So the best way to be a student is to be a teacher, by the way, and particularly in that space, because if you want to understand quantum computing and other fields like quantum cryptography and quantum sensing, you need to learn different fields. I mean, you need to learn about classical computing, because if you don't know anything about classical computing, you won't know how you can be better with quantum computing. You need to know about software design, algorithm design. Then you need to know about the physics and the engineering of those systems to make sound comparisons. And what amazed me in that field is there's so much science involved there. I've never been so happy to look at the science of that field, because it's so diverse. And then I looked at quantum chemistry like you. And so that was the fun of it, look at all the scientific fields. So now what you need to know, I'm not sure. Well, what you need to know is, like it was said before, quantum computing is probably not going to revolutionize IT, like we would say, like AI right now. You have to understand the nitty-gritty details of what it can do, what it can't do. And I would
there's going to be a coexistence in the future.
Yes,
between classical and quantum. That slogan is accurate.
Yeah, but based on the earlier presentations, I would add something. Usually, we always have a discourse about speed up on quantum computing. And when you look at the algorithms that are around, particularly in quantum chemistry, you discover that the benefit of quantum computing is not just speed up. And sometimes you may not have a speed up, but you might find something else. Mm-hmm. And what is the something else? One is the quality of the solution you're going to create. So, for example, if you do a quantum simulation, a chemistry simulation, but you've got a much better accuracy, the quantum chemists, they love it, even though it's the same computing time. The second can be heuristics-based optimization. So if you have a better heuristic to find a better solution, the same. It's going to be a benefit, even though it may not be as fast or faster. The last one, maybe it's linked to one of the things I co-founded recently, the Quantum Energy Initiative. Maybe you're going to end up with having a lower cost or lower energy cost. Maybe. It's still an open question. It's a research question. You have to look at this. Most physicists, they have some kind of insights of maybe you're going to have some energetic advantage, but it's not true, because you have all the overhead of quantum error correction, which adds a lot of burden to those systems. But it's an interesting question. So in the end, the business benefit of quantum computing is going to be a mix of that: speed up, quality, energy, cost, and maybe to some extent, typically for quantum machine learning, even though it's kind of dubious domain, maybe we can be able to do interesting machine learning applications, not LLMs, definitely not LLMs, but interesting machine learning solutions with fewer data, less training data. One of the reasons is quantum computing algorithm is, a little bit better than classical computing algorithms to explore a large data space. So this is some kind of benefit you could get from a quantum computer.
All right, Will, what do we need to know as we kick off the day?
Well, I think a few things. One is that quantum computing is real. It's not fantasy. It's happening right now. It's still early days, but I think that we've had our, for lack of a better analogy, our Wright brothers moment, that plane has flown. And I say that because for me that metaphor is meaningful in the sense that when we look back and we see that picture of the two Wright brothers flying their plane, we say, okay, yeah, that was the dawn of commercial aviation. And the second thing we probably think is, I'm not getting on that plane, right? So the point is that That was the dawn of commercial aviation. We knew it was coming. It might take 10 years or 20 years or 30 years. In fact, it would take all of those years. And that's another point to make, which is that, for example, when Jensen Huang said a month or two ago, right, that, they asked him, when are we going to have a quantum computer? And in his mind, he was thinking a quantum computer that is super performant. It's going to revolutionize the drug industry. He's thinking of a highly mature quantum computer. And he said, on the early side, 15 years, maybe on the long side, 30 years. And of course, quantum stocks tanked. I was actually quite happy. I'll tell you why.
You'd shorted those stocks.
No, I wish I had shorted those stocks. I was happy because, I've been in the field for 20 plus years. And I think that if you had asked Jensen, I respect Jensen, incredible technologist. If you had asked him that question 10 years ago, I think he would have responded very differently. I think he would have said, yeah, maybe when hell freezes over. Oh. Or maybe, yeah, that'll happen right after fusion, right? But he didn't say that. He said, within 15 years on the early side and 30 years on the late side, we are going to have a highly performant computer.
The 747, to keep your equivalent.
The 747, right. That's right. That's exactly right. And we know that there was
the only thing I've ever gotten exactly right about quantum technology.
That's not true,
it will
Andy.
never happen again.
That's not true. But there was a good 50 years between the planes of the 1930s, which were commercial, generating revenue, generating value, and the planes of the 1970s, 80s, and 90s, right? And so we need to keep that in mind, is that it's not a step function. Quantum computers aren't going to be just laboratory curiosities, and then one day, bam, we're solving the world's problems.
It's not going to be a quantum phenomenon.
It's not going to be a quantum leap. Yeah, exactly.
Got it.
I think that's important to remember. And there are companies, I was reminded even Wednesday night, that are generating revenue today. That is true. They're selling time on small quantum computers. They're very small. But you can use them to learn how to do algorithms, what algorithms are going to be important for your business. You know your problems. How is a quantum computer going to solve your problems? You can then understand, okay, these are the algorithms that matter for my company, and they'll affect my bottom line in the future. And it also gives you insight into what we're waiting for. Am I waiting for the 1930s plane? Do I need a jet airplane? Do I need a Concorde, right? That insight is tremendously valuable because it gives you an advantage over your competitors. And I think that this is what's happening right now. That's how a lot of these companies are generating revenue and value today. Last thing I would like to do before I forget, if it's okay, where is Yingjing in here? There's Yingjing. I want to introduce Yingjing. She's the senior program manager of the industry membership group for the Center for Quantum Engineering. And also like to welcome folks from Dell who are members and perhaps others. If you would like to learn more about our industry membership group in quantum, please talk with Yingjing. We set this up precisely for this reason, which is to introduce companies to quantum computing, work with folks at the MIT campus, and start becoming quantum aware in your quantum journey.
Will, what was the equivalent of that Wright brothers' first flight in your eyes?
So it's a little fuzzy, but I think in 2019, Google had a demonstration with a chip they called Sycamore. And they did something called random circuit sampling, which is not a commercially relevant algorithm per se, but it is a case where you could actually compare a quantum computer with, say, 53 qubits in that case, and the top one supercomputer in the world at that time at Oak Ridge National Lab. And what they said in the paper is that, okay, what we can do in about 300 seconds would take this computer, 10,000 years or something. Mm-hmm. Turns out they weren't quite right on that. That over time, now to their credit, they did say in the paper that, classical algorithms will improve and that over time this may catch up. And it was true that by today, we can do on a laptop, what they did on the 53-qubit quantum computer. But nonetheless, I still view that as perhaps the Wright brothers' moment. And the reason for that is because for the first time, we could say, in this corner, quantum computer. In this corner, number one supercomputer in the world. Let's have a bake-off, right? And the point is that 53 qubits, 100 kilowatts of power, 300 seconds, versus 40,000 processors, 10 to the 18 transistors, an equal number for memory, 10 to 100 megawatts of power, right?
Yep.
Just what Olivier mentioned is that it's not just about the speed. And the other thing I'll say is that in the intervening years, both at USTC in China, and also, again, Google last fall, now with the Willow processor, they're just increasing by a few qubits, 55, 60, and then at last fall, 72 qubits. And now, undisputably, that random circuit sampling problem on a quantum computer with just a couple more qubits. I mean, they were right on the edge in 2019. And now, I mean, it's a ridiculous number, like 10 to the 24 years. You know, much longer than the age of the universe. Right?
Okay, so at the start, as you were describing that progression, I found myself underwhelmed, right?
Yeah.
We've gone from 53 qubits to 72. I didn't feel like leaping out of this chair and applauding at that. You're kind of telling me I should.
I think you should, and because when you think about quantum computing and its advantages over classical computing, this is exactly what it is. There's a double exponential win, at least for the types of quantum computers that use, say, silicon manufacturing. So the first exponential win is the same one that helped us with CMOS, is that, Moore's law type scaling. We have that tool set, we can make exponentially more transistors, exponentially increase revenue. But the second is that every time I add 1 qubit, I double the size of the state space.
That is a useful rule of thumb.
That is a useful rule of thumb. That, by the way, that's true for classical computers as well.
Okay.
But classical computers can only represent one of those states at a time. The quantum computer can be in a superposition of all of those states at a time, right? And so you're not just increasing the size of the state space, you're increasing the usability as well. And that's an exponential gain. And so going from 53 to 72 is a exponential improvement.
It is a big honking deal.
It's a big honking deal.
But it's hard. It's very hard.
But it's very hard. No,
Yeah,
let's not kid ourselves. It's very hard. You have to learn how to take advantage of that. Mm-hmm. The second demonstration, also from Google last fall, was quantum error correction and the scaling of quantum error correction. And we can talk more about that, but basically, to realize the full promise of quantum computing in the future, we need to correct for errors faster than they occur. And what Google showed is something that Peter Shor here at MIT, Calderbank, and Steen showed is that in the 90s is that, look, there is a quantum version of error correction. Real systems use error correction all the time, right, to improve reliability. From faulty elements.
This is not some unique Achilles heel of quantum computing.
No, that's right.
All the time.
We do it all the time, particularly in communication systems. But if you remember ECC on your memory, that is actually classical error correction, fixing memory errors. And what Google showed is that they went from a distance, something we call a distance 3 code, to a distance 5 to a distance 7. They increased the number of qubits from 17 to 49, to 97, and these are faulty qubits.
Okay.
And you might think, well, if they're faulty, it'll get worse and worse and worse, but it didn't. It got better and better and better. And that's the side of the line you need to be on. And the way that I think about it is in terms of teamwork. And in fact, many of us have had kids, right? I have a son. He was a kindergartner once, and I remember him playing on the playground with other kindergartners, and brings joy to my heart when I think about it because they're running around, it's chaotic, they're having a great time. But if we add more kindergartners to that picture, what's going to happen?
Chaos will go up.
The chaos is going to go up. That's exactly right. But at some point during our education, we cross a threshold. And the threshold that we cross is we become more and more performant and educated. And at some point, I don't know exactly when it is, we can form teams of people and they outperform any individual. And that's the concept of error correction, is that once you make your qubits good enough, they're not kindergarten qubits anymore, they're maybe 5th graders or 10th graders, right? Now you can add more and more people together onto your team, which we call a logical qubit, and the performance gets better and better. Yeah, and you think about it, all of these sophisticated organizations we have in the world today are comprised of large numbers of people.
And they're error correcting.
And they're error correcting, and they don't come for free. Of course there's an overhead. You make a company with 100,000 people, you need an HR department, you need all sorts of things to help it work. So you do pay a penalty by increasing the team size, but with quantum, the gain you get is also exponential.
All right. Well, I want to build on a couple things that you said. You mentioned some announcements that have come out over the years. Yes. And I guess that I've done enough kind of web browsing and Googling around about quantum computing that my Google News feed now has a special section devoted to the latest breakthrough announcement from the quantum technology world. Right. And every day there's a screaming breakthrough kind of announcement. Can each of the three of you give us your newbie's guide to reading those announcements and being able to separate signal from noise, the wheat from the chaff? How do we know what's a real breakthrough if we're just trying to follow the news? Carla, I'm going to pick on you to start.
Oh, geez. I think that, my natural reaction is to be honest, just take kind of a skeptical view.
So just ignore all of them.
Not
it's
ignore.
A really simple algorithm.
You just have to you have to understand that there's real potential in the space, and people want to capture, the potential where they can, right? And they want to be a part of the ecosystem. And this is not new. If you're part of this ecosystem, I guess you become hardened to it, right? You in the early days about announcements of wonderful machines that were going to, solve all these problems that have never come to pass, right? And still haven't come to pass.
So what kind of headline would actually make you go, holy Toledo?
So some of the recent headlines that, have been upplayed and downplayed in the market, like Microsoft's progress on the new topological qubits and the Majorana particles, that is really interesting to me, right? That is another player in the game that, has been around for a while, but has made significant progress and can offer us another modality. Because we still, it's like VHS versus Betamax right now. We didn't know, one of these technologies might have been better. Betamax might have been a better solution, but VHS won because it fit the market niche more efficiently, and it got the momentum that it needed. And so we're in this delicate phase right now where the funding that goes into these systems matters. The announcements that they make at capability level matter, and so those things are very interesting to me. Is like a qubit count increase is really, really good, but an error correction increase is much more interesting, or new error corrective algorithm that allows you to do more things with a system that exists today. Right? I think we talk about this in terms of quantum utility. Right? Is how useful is the thing that has been announced going to be, and not what fantastic potential does it have, but how useful is it going to be now in order to get us to the next stage of usefulness, to get us to the next stage of usefulness. That's kind of how I look at it.
Olivier, what's your newbie's guide to the press release?
Yeah, I try to be cautious, obviously. There are many ways to. First, you need some technological background to understand all these announcements. The way the stuff I do is I try to have a holistic understanding of what it's all about. So let me give you an example about the Majorana announcement from Microsoft. I'm not enough specialized in condensed matter to identify if their TGP protocol works well or not, and there's really a topological phenomenon. What I do look is the rest. I look at control, electronics. I look at how do you size the chip. I look at how do you manufacture it, and I look at all the components in the whole system. And there you find interesting things. You can find, I say, loopholes in the architecture, and it's not discussed about. Another example, which is more an upside of what I see in the industry, is I look at all the components. And for example, I look at control electronics. In the case of superconducting qubits, there are a lot of advancements there. Cryo-CMOS, so-called superconducting electronics, so-called SFQ. There are many people here in the US working on that. And there are many ways to improve the scalability of the systems. Because, for example, what Will told about error correction, there's a huge overhead. When you compare to classical computing, it's not just a ninth bit of parity in telecom. So you have an overhead that's from 1 to 5 orders of magnitude in the number of physical qubits. So it's got a cost. And so what's interesting is to look at what people are doing in labs and in companies to reduce that overhead. And one example to reduce that overhead is to improve the connectivity between the qubits. Because when you improve the connectivity at a physical level, you reduce by at least one order of magnitude the cost of the error correction. So typically you do that with trapped ions, with cold atoms. We can do that potentially. I think you work on that with superconducting qubits, with special layer connecting with microwaves, the different qubits. And there are many ways to improve that. So it's a mix of physics problems and engineering problems all together. And how I would describe this world compared to other worlds I was in before, I look at AI, I worked for a while in AI, I worked in the semiconductor industry, I worked in digital television in the past, in genomics, many different things. And the special characteristic of this industry is, I would say, it's a huge experiment where we parallelize everything. We parallelize physics development, and there are a lot of unknowns in that space. We don't know what's going to happen when we have a lot of zillions of physical qubits entangled together. We don't know what's going to happen. We even don't know if Schrödinger's equation will still be valid to some extent. We have engineering developments. We have business developments, and we have people like my neighbor developing applications all together. And if you look in the past, let's take your smartphone. When the smartphone was developed, let's take the iPhone from Apple in 2007. It was just the early stage of 2.5G, then 3G came out. So all the telecoms were investing a lot in infrastructure. So it came in parallel between the infrastructure and the smartphone. But we didn't have applications, really. The applications came later. Here, we are upside down. We have more applications available, although some of them may not be that useful, but more applications and hardware to run them. Twitter didn't come before the internet. I mean, Facebook as well. So
this is the first time the software is kind of running ahead of the hardware.
Exactly. We are in an Ada Lovelace situation if we compare with history. So,
Will, what's your newbie's guide to reading the press releases?
Yeah, I mean,
Do outsiders have any hope?
Of course.
tell
I
us.
mean, okay, another shameless plug. I mean, we've developed professional development courses here at MIT in 2019, and now we're making an executive version of it. But 4 courses, 4 weeks each, online, meant for people who did not do a PhD in physics, right?
Which is most of us.
It's meant if you want to pivot to quantum, you want to learn the jargon, understand what's the hype, what's the reality. These are great courses to take, and we're happy to tell you about them in more detail. I guess 2 points I would make is that, you should be skeptical of the weasel wording. Be very careful. It reminds me of my grandmother. I won't. Oh, okay. Shall and should, can and could, will and would, may, might, must.
The verbs matter.
And do, did, does. Right? It's like she was an English teacher. It's important to read. They're all going to start breakthrough in quantum computing. Okay, but then for the Majorana result. To pick on Microsoft. And I appreciate what Microsoft is doing. They've spent a lot of money, a lot of time. They're taking on a very hard problem, and I'm glad they're doing it. But what the press release said is we are releasing Majorana 1, a chip capable of 1 million qubits, a design of 1 million qubits. And then you're like, okay. And I've had many people write to me saying, wow, did Microsoft make a 1 million qubit chip? And I have to tell them, no, they didn't. They don't even have 1 qubit on there. Right?
But they have room for 1 million.
They have room for it, and they have an architecture and a design that's capable of 1 million qubits when they can get the qubit to work. Right now, okay, I'm not picking on them. I think it's great that they've made they published a paper in Nature. Another one's coming out. They're making tremendous progress on the science and the physics of it.
Right.
But the problem is when they do the press releases that seem to imply more. Right? And it's intentional, right? Do we have full self-driving? Right? What does that mean? Right? Is it autopilot? Is it full self-driving? Is it there yet?
But you're decreasing my hope that I can ever read these things intelligently, because I have this heuristic that if there's a paper associated with the press release in a top journal, that's the thing that we should pay attention to. And you're kind of saying yes, but no. There is a Nature paper associated with the Microsoft, but it's still capable of versus having.
Yeah, that's right. And I think, just recognize that there's a lot of hype in the field because there is so much promise to quantum computing. But that promise, of course, drives the hype. And it's just
let's not be naive. That's the kind
right.
of thing that happens.
Second point, just one other quick point is that what's very important with quantum computing to remember is that it's not just the number of qubits. With classical computers, it's great, right? Because transistors are almost perfect. The error rate's like 1 part in 10 to the 20. So you go to the store and it's more like, what's the clock and how much memory you got? Because I'm not worried about the transistors. I know you got a lot of them, and I know they're all going to work. Wow. But with quantum computing, it's not that way at all. And so you need to ask, how many qubits do you have? Also, how good are those qubits? What is their error rate individually? And you'll find that the largest numbers of qubits tend to have lower error rates. Higher error rates. Sorry, you're right. Lower performance. And okay, that's natural. It's early days, right? So it's not just the number. I think, in these announcements, just remember it's not just that, okay, it's capable of 1 million qubits. That's great. I'm glad that it's capable of 1 million qubits. What is the performance of each qubit?
Okay. When I read my press releases, I notice they seem to come from. I'm sorry, Olivier, you wanted to jump in and say something.
Yeah,
Go ahead.
I would like to jump in on another kinds of announcements, which are related to case studies and algorithms. So it's not hardware related, it's a case study. So it's business, as the title of this conference is about. So there are also ways to decipher what's in those papers. So one of the ways I proceed is I'm looking at the missing figures of merit. So for example, if there is a paper saying, we have a better result, I say, what's the computing time? Because it's not in the paper. Usually it's bad news. Oh. And the other way around. So you look at the missing holes. That's one key thing to do. And the other thing is, how is it compared to classical systems? And typically, there was a paper recently, I think by IonQ, which was comparing something with 36 qubit and a PC that cost $2,000. And the improvement was about 12% speed up. So I say, what's the price of an IonQ machine? So sometimes if you just look at the raw numbers, price, computing time, improvement, you find that it's not yet right. But then you have to look at the roadmaps of vendors. So what are going to do in 1 year, 2 years, 3 years? And maybe at some point they're going to bring some benefit. So learning the case studies is as important as learning about the hardware progress that's being made. And it's a different discipline. I'm currently writing something on that. I found 12 tricks that people are using in those papers. Tricks. You see what I mean? So,
I just add one thing. I totally agree with Olivier here, but I also want to mention that, it's very early days. And for me, having been in the field for a while, as I mentioned earlier, it's fantastic that we're at a point where we can have this conversation where we're saying quantum computer, laptop, right? We couldn't have that conversation 10 years ago, right? And so it's still early days, there's a lot of hype, but we're actually having a serious conversation about how much better a quantum computer is than a $2,000 laptop.
There's something else, which is the progress from classical systems.
Yes.
The thing you described at Google being done in 6 seconds now on a classical system.
Yeah, that's right.
Now it's 6 seconds. It's in Google's paper. Yeah. What they did in the comparison with 10,000 years, 6 years ago. Now it's done in 6 seconds in the classical system. Maybe not a laptop, but depends. Yeah. Really, we have to look at the progress in classical systems. There's a technology called tensor networks, which improves the way you compute matrices, so complicated computing for optimizations or even quantum chemistry. So there's a lot of progress in that space, of course, with GPUs for NVIDIA and Cerebras and others. So quantum computing is, let's say, competing with a moving target. Right. And it's good because it's helping everybody making progress. So another example is AlphaFold. The famous AlphaFold software from DeepMind, it's a UK branch of Google, which does many things. AlphaFold is able to fold proteins to an extent that was not thought about 6 to 7 years ago. And I remember when I started 8 years ago in quantum computing, I dreamt about protein folding with a quantum computer. But now the classical system is able to do that. So it's moving the needle somewhere else on what the quantum computer will be adding as a value. So doing more bottom-up quantum simulations based on Schrödinger's equation, knowing the ground state system or so-called dynamics of a quantum system, which may not be possible with machine learning. So there's kind of competition between machine learning and quantum computing for some respect.
When I read my press releases, they seem to come from 3 different categories of company. The first one are companies that have been around for a long time, like IBM, or I still keep hearing about quantum contributions from Honeywell, of all things. So there's like some very old economy companies are hanging around there. Then there's the names that we've been talking about. There are the Googles and the Microsofts and the Amazons, the current tech giants. And then the third category are companies that I rarely heard of, with a couple exceptions like D-Wave. This new generation of quantum from the start startups, right? Can you handicap this horse race for us?
There's 90 companies in that space.
Okay, which of those three categories is going to dominate the landscape?
Or in the future? Well, somebody we didn't mention, the cloud providers. I'm thinking the Amazons and Google of this world, probably.
I think I mentioned
Microsoft.
both of those.
Yeah, but I mean, the guys who control the access for the customer. So, Bracket for Amazon may be a powerful tool. Qiskit from IBM. So, what we underlook right now in understanding the business structure of that new domain is the way middleware, compiler, software applications are going to be layers.
So you're kind of voting on the current tech giants.
Not necessarily. Right now, it's more giants who are powerful in that space. But we see the emergence of smaller players which are very specialized on niche products. Let me give you a couple names which are, by the way, outside the US. One is Quantum Machines. So it's a company you know well. Yep. So these guys, they are doing control electronics and the software that controls the qubit. And they are dominant. They are more than 300 people. They have half of the market. It's an Israeli company. Another one is Riverlane. It's a UK-based company. They are a worldwide leader in so-called error detection, to make it simple. Another one is Q-Control from Australia. They are leaders in error suppression, which is another thing to do. So you have a lot of companies. Another one, which is obviously famous, is Blueforce, which is a leader in cryogenics. It's the worldwide leader. It's a Finnish company. How come it's a Finnish company? It's a Finnish company. They have 75% of the market. So you have a spread of the value across multiple players around the world, which are very specialized in software, in enabling technologies, in hardware, even in cabling. If you want to buy a cable for his fridge, there's only one company in Japan, more or less, to do that. So that's an example.
Carl, how are you handicapping this horse race?
Well, this is kind of goes into what I said earlier. We don't know which modality is actually going to be beneficial in certain ways. And each of those categories has...
This kind of surprises me, right?
Yeah,
like, for example, well, you've been doing this for 20 years. How do we still know so little about this whole thing?
I'll answer. Go ahead and finish, and then I'll jump in, yeah.
I mean, each of the categories that you mentioned has companies working in each of the modalities. And so it could be that there are multiple winners across the categories, and we have to pay attention to all of them, really.
How are you allocating your hypothetical quantum portfolio? Is it the old guard, the modern tech giants, or the crowd of newbie startups out there?
I mean, I guess I just have the luxury of getting to work with all of them, and so that's my approach.
That's the most pathetic dodge of a question.
I know, but I mean, I can tell you examples of, like, direct examples from each of those parties in each of the groups where I've worked with a company, a startup, and built an application, or I've worked with some of the giants. We work closely with the enabling technology companies and the middleware layers. We work closely with, Honeywell you mentioned, which is now Continuum. We had some of the pre-release access to some of their the first time they had mid-circuit reset. For example, they came to us and said, "Hey, can you work with us and develop a use case on top of it?" And so this community is well connected and it's willing, and people know what's going on with one another. There's actually, enablement and help from the tech nut giants to the startups to get access to their product. Like, we're all working together here, and I think. It's very hard to know. Am I hearing
correctly that you won't be surprised if in 10 years it's, for example, Google that's dominating the quantum technology landscape, or in 10 years a company whose name I don't know right now that's had the big breakthrough and is dominating the industry? Would neither of those surprise you?
I would say at this stage it's very hard to make that prediction.
Will?
Yeah, you would ask why all these technologies? Why don't we know which one's going to win?
Yeah.
Yeah, and I use an analogy, if it's okay. The field effect transistor was actually invented in the 1930s.
Okay.
Yeah, okay. Before we even had the transistor, right? People were trying to do it. The schematic was there. Yeah. We invented the transistor in 1947, Bell Labs. Okay. The first computers were made from vacuum tubes. That transistor didn't work very well. And vacuum tube computers went on for a good 10, 15 years before, okay, this bipolar junction transistor, as they called it, got good enough that people soldered them together, and okay, now we have a transistor-based computer. But it wasn't until the late 50s that we had integrated circuits. But having an integrated circuit, if you look at that picture, you're like, wow, one transistor on a chip this big, right? So then it wasn't actually till the 70s that Intel made the 4004 processor, and that's when it really started to take off. My point is that technology evolves, right? And what we do is we make the best decisions we can with what we know is working at the time. That's rational, right? And so in the 50s, vacuum tubes work, transistors are faulty, I'm going to go with vacuum tubes, right? And I think that this is how it worked with quantum computing, is that there are all these candidates coming out of universities. But the ones that were most performant first were the superconducting qubits and the trapped ions. And it was natural that those two would get the funding first. This is hardware. I mean, it's very broad. It's not just hardware, but it has a very large hardware component. And that means it's capital intensive. And so the big players like IBM and Google and AWS have the pockets to actually put the investment in that's needed to do it. I have a startup. I'm a co-founder of Atlantic Quantum. And, what we focus on is solving a specific problem. For example, in our case, it's reducing the cost per qubit. Okay, that's going to be important in the future, right? And I think many of those 90 companies that are startups, they're focusing on specific problems. They may not phrase it that way. They may say to their investors, we're a full stack quantum computing company. But basically, they have one or two really good ideas, and they're capitalizing on those. And the question is, are they going to become a unicorn and then become the next Intel? Okay, we know that that's unlikely. Oh, I think so. All right. Personally, that's my opinion. Will they become a unicorn? Probably, right? But will they become the next Intel? I don't know, because again,
it's because of capital intensity.
Capital intensity, and also the breadth of the problem. Again, many startups are focused on, I know how to do this thing really well, and I'm going to do that better than anyone else. And they get the good press release, and they're like, okay, we can now control 300 neutral atoms, and we can encode 20 logical qubits. And you're like, wow, that is a step function improvement on where we are. Okay, but now there's the other 9,999 other things I got to do before I become Intel, right? And so it's not to say that these startup companies are going to fail. They might succeed at becoming the next Intel. But to my mind, the most likely outcome is that they solve specific problems, and then they become acquired by larger companies, for example.
So I'm hearing that your hypothetical quantum portfolio is allocated probably mainly toward that middle bunch of today's tech giants, with a healthy sprinkling of the startup ecosystem. Because like you say, some important companies will come out of that.
That's right. And if you're an investor, I think you think about, is it early stage? How much patience do I have? Am I a growth investor? Do I want to see a return in 5 years, or can I wait 15 or 20 years? And that would determine whether you sprinkle a little bit across a broad range of companies, or if you focus on a few. And of course, I'm not advocating any of that. I'm just saying that these are the things I would think about if I were an investor.
Olivier, what is your? Okay, you go, and then I want to hear. No, hold on. Let's get Carl. Hold on, Olivier, Carl first, and then I want to hear your portfolio.
Well, I mean, I just think that the caveats to that are, if you look at the investment that's coming out of government, it's typically being directed to the smaller companies, which are allowing them to access and to get caught up to, in some of the cases with hardware where they're maybe at a disadvantage. That's one thing. And then, there is assistance from the larger companies within the community to help elevate the startups, because they see a diversified portfolio as part of their play as well, right? As if it's bracket, access to multiple different types of devices, because it drives a different revenue stream for them. So they're incentivized at least at some level to play nice. And so, I just think that it's a big story.
Oh yeah, and I didn't mean to imply that we don't need any of it. I think we need all of it. Don't get me wrong. The big companies are so focused on scaling up that they don't have necessarily the time or the bandwidth, right? The funding even to do all of the breadth that those 90 companies are covering. So it's all important. You need that ecosystem for sure.
Exactly, and as Jonathan mentioned earlier, the guard so to speak, is starting to change with QEra and some of the photonics companies coming up as viable competitors to where we, as we had made a lot of investment in ion trap and in superconducting before, we're seeing that market, mediate and shift itself a little bit. And I think that's really interesting too.
For sure. Yep.
Okay, Olivier, how's your quantum portfolio?
I will share 3 ideas. One is the companies I'm looking at are those who are reducing significantly the overhead of error correction. So, for example, self-corrected qubits are very interesting. The ones from Norcantic in Sherbrooke, from Alice and Bob in France. Those who are reducing this overhead, which is very significant. So it can be an interesting ploy, I would say. And I look at all these dimensions, so connectivity between qubits, like we have with ions. That's one of the ideas. The second is, I think that in the future, we will need many of these technologies altogether. Let me give you a couple of reasons. One is a full-fledged quantum computing system is going to need a computing system with qubits for calculation. But at some point, you will need quantum memories. And the technology to do quantum memories, they may not be the same as the one for computing. And then you will need communications. But communication not in the sense of QKD and cryptography. It's how do you connect those systems together? And you will need to connect those systems together for multiple reasons. One is a scale out, so improving the power of a system with assembling multiple QPUs. But there's other reasons to do that, for security reasons, for example. You can imagine an architecture, it's called blind quantum computing, where you have a small quantum computer that's connected through photonic links to a large one, and the connection is highly secured through the cloud. So then you will not have the same concern that we have today when you send your data on the cloud from Europe to the US or whatever. And you have this Cloud Act and all these protections. So natively, quantum computing will protect your data because you will have a quantum communication between the two parties. So you will need 3 technologies. And at this point in time, I think that no qubit modality is able to do the 3 well. Probably, at least for communication. Communication, it has to be photons, optical photons in the infrared spectrum. Storage, maybe a mix of cold atoms, ions, NV centers. So it's typically technology which seem to be better to do that. And computing, maybe silicon, superconducting qubits, which are faster because you need good speed. The last one I would like to mention is Intel, this Intel thing. There's one reason I don't believe there's going to be an Intel of quantum computing, which is at least at this point in time, we don't have any expectations to create a consumer market with those products. These are going to be back-end products, so products that are in data centers on-premise with customers. So it's not the same volume. So we may build maybe a small NVIDIA because NVIDIA is a back-end company, even though they have GPUs for game consoles and gaming PCs. But the bulk of NVIDIA's revenue now is on servers, definitively. So it's going to be a server business, a data center business. And there is a connection between the stuff I'm saying here and the algorithms. The concern I have is the bulk of what is credible right now is quantum chemistry. Because we know algorithms which can bring some speed up and some improved quality. But this is applied research market. So it's, I would say, middle-sized markets, not narrow, but middle-sized. The biggest market is business operations from companies who want to optimize financial portfolios in banks, want to optimize transportation in logistics and whatever, retail. Those companies who have a day-to-day business operations. That's the largest market. But at this point in time, we don't have many algorithms which are bringing real value there. There's some innovation required to invent new algorithms. So that's where we still have stuff to do in the software side. Because we are not there yet. So there's a lot of uncertainty in the connection between hardware, software, applications, market size, and it's about economics in the end.
All right, so let's broaden this out to the geopolitics of quantum technology. And Olivier, you mentioned a bunch of different startups, several of which are headquartered in Europe. Is quantum technology going to allow Europe to kind of catch up to the US's tech ecosystem?
I hope so, of course. I hope
what do you think?
Well, okay. I take for granted that the US are the largest. It's the largest country, the largest GDP, the largest investments. You have those large companies like IBM, Google, and Intel. We don't have those in Europe, so we are not on par with the US. But Europe.
Let me underscore how big the gap is right now, because the Draghi report came out last fall and was really just a very blunt document about how far behind Europe is.
In the digital economy, at least.
For example, you mentioned the lack of tech giants.
Yep.
Draghi went a step further and said that there have been no European companies founded from scratch in the last 50 years with
15.
50 with a market capitalization north of $100 billion. Whereas in the United States, you could lose track of them.
At least.
So my point is that the gap. Let me finish. But my point is that the gap is actually quite large right now. Yes. And so my question for you is: do you think quantum is going to help shrink that overall tech gap?
Well, quantum is a new opportunity for Europe. That's why there are plans. And something you may not know is Europe. The EU plus member states, they invest more in the public sector in quantum tech than the US. The gap is about $1 billion every year in the US, at least in the NQIA plan. And in Europe, it's about $9 billion over 5 years. So it's nearly the double. And China is probably between 4 and 5 billion over 5 years. So Europe is investing a lot in the public. When I mean public, it's public money that funds academic research, that helps also startups to strive, that organize the ecosystem. So, but we don't have the same funding mechanism in Europe, and there's a kind of gap there. But when you look at the top 15 companies in the world, there's about 3 which are in Europe, which is not that bad, compared to what we have usually. So we have Alice and Bob, we have Pascal, we have IQM, which is a very large company based in Finland, as well as Bufors. We have one of the strengths we have in Europe is enabling tech companies. For example, one of the worldwide leaders in lasers is Toptica. It's a German company. They're much better than the lasers that come from here in the US. So cryogenics is the same. Cabling, we have Delft Circuit, we have Q-Blocks. We have many interesting companies in Europe. Another one, which is not directly related to quantum, but which you have to know, ASML. ASML, it's a $27 billion company based in the Netherlands. They are the worldwide leader in so-called EUV, so extreme ultraviolet photolithography for creating CMOS circuits. It's a monopoly. This is the only company doing this product, being used by TSMC, Samsung, Intel here in the US. So it's a European company. We have SAP, we have Dassault Systèmes, which is the worldwide leader in CAD/CAM, so computer-aided design software. We can build companies, but it takes time. And one of the reasons
all those companies you just mentioned are more than 50 years old. ASML is a result of a merger.
Well, ASML was created in the mid-'80s. Dassault Systèmes was created in 1982.
It's a result of a...
It takes a while. But even TSMC...
You've had a half century.
Yeah, TSMC was created in 84, 86, something like this. So most of the large companies were created a long time. Microsoft is celebrating its 50 years anniversary, 75. So 75. It's the same. So 50 years old companies are the leaders.
Come on. NVIDIA, OpenAI, Google.
Of course, they are younger.
Well, these are quite young companies. My point is, again, the gap is quite large, and I'm just wondering if quantum is going to shrink that gap.
Who knows? You always have to build hope wherever you are. So the hope. Look at this. The investment in science in Europe is significant. Yep. We have many Nobel laureates. We had Zeilinger, we had Alain Aspect, and Olivier recently. So we have a lot of Nobel laureates. There's good science. So the hope is that good science and good engineering can bring some value, but there are 2 things to do. One is Europe has to team up as a continent, not just isolated countries. So I saw the order where we had France, Germany, Netherlands. We should count Europe as a whole. And there's going to be some consolidation required between enabling tech vendors, some qubit vendors. We need to behave as a continent, not as a split countries. Mm-hmm. And then probably at some point there's going to be some new partnerships to invent between Europe and the US. Even though politically it's...
This is not the golden era of transatlantic partnerships. Those seem to be heading in the wrong direction. Carl, can we broaden this out and talk about again, as we talk about the geopolitics of quantum, can you talk at all to the race which is pretty clearly going on between China and the US with quantum?
Not in any great detail, unfortunately. It's not an area that I specialize or focus on. I think there are a couple of things, though, that are interesting within this ecosystem that we can't talk about. So there is the quantum networking outside of just quantum computing, where the U.S. has put out national security advisories that say, quantum network for security is less interesting than using PQC. And so that's opened the aperture for China and Europe to spend a lot more time on this because, there's kind of been a broad message from the government to wait and use classical technologies to solve this problem. And so I think that has heated more opportunity investment in other regions as well. And, we've seen China make a lot of breakthroughs in having the first satellites that do quantum communications and having the largest networks that do quantum communications over the longest distances. And so we're, I think in a catch-up mode because, we handicap ourselves in certain ways. Now, that could be argued, but you see some of the bigger announcements, bigger numbers, and more progress in other locations, as far as what I'm understanding. And so, I'd love to talk about that a bit more. I don't know if you guys have perspectives as well.
Well, where are you on the race between the U.S. and China, or is that the right way to think about it?
Well, if we're in a race with China, it's pretty early in the race. I think I would say that, first of all. And, it touches on what we were talking about earlier about which modality is going to win.
Yep.
Okay, and if I pull ahead at mile 5 of the marathon, what does that actually mean? Okay. If I take a step back and just look at what China's approach is to quantum computing, I think more generally also, and the U.S. approach to quantum computing or technology development more generally, there are some broad brush differences. I want to emphasize broad brush because it's not, China, of course, is more of a command, direct, top-down driven decision-making place. And so it's not surprising that they can make a bullet train in a year that runs from Shanghai to Beijing because they just say, hey, we're going to do this, and they do it.
Your house is in the way, and that's not really a big problem.
Yeah, that's right. It's eminent domain. So, and I think similarly in quantum, they have selected a few top people, and in particular, John Wei Pen is going to lead this effort, and we've got a big pyramid, and we're going to move out. And as a result, they're moving out very quickly. They give him money, he makes decisions, and they do it. What they don't have as we have in the U.S. is necessarily the VC and an investment environment to take those results and commercialize them necessarily, right? And I think that's one reason we don't see a large number of startup companies coming out of China in this space. There are a few, but not many. And in the U.S., it's almost the opposite. It's almost, in some sense, comical. Is that we have so many different agencies, and they're all doing their own thing in quantum, and they get together once a year and coordinate. But then basically DOE's doing this, NSF's doing that, Commerce, DoD, intelligence community, and they fund a lot of people, and do a lot of things, and it looks disorganized, and you're like, how can this ever work, right? But actually, that's the secret sauce, in my opinion, because it explores a large space. Things that are going to fail fast. Things that succeed start to rise up. Okay, then there's a refocus on those things, spread it around, do the same thing, and eventually you narrow down very quickly. And we also have the investment culture, right, to take these things out of places like MIT and Kendall Square and try to commercialize them. Same story. Spread it around, fail fast, things that work rise up. So and time and again, I think historically we would say, okay, this approach seems to work. Will it work for quantum? Okay, we don't have a crystal ball, but I would put my money there.
But you're kind of long on the broad approach.
I am.
The broad U.S. approach, more decentralized, maybe a little more chaotic, maybe a little more redundant. But like you say, the bad ideas fail quickly and the good ideas tend to percolate up.
I think so. If I had to tweak for that, I would tweak from that point rather than try to tweak from the opposite case.
Okay, I got it. Are you worried, though, that one ingredient in the U.S. innovation ecosystem has been, as you say, funding from lots of different parts of the U.S. government?
Yes.
And since January 20th, it seems like that might be changing. Is that something we should be worried about?
I think it's something we should keep our eye on. I think it's too early to say if we should worry about it. And to some degree, it's outside of our control, right? And so should we be worrying about things we can't really control? We should focus on the things we can control, right? I think we have to wait and see how this plays out over the next 6 months to 12 months. Yeah.
Yep. I want to go back to something I've heard, I think, all three of you talk about, which is that when we think about the race between quantum computing and classical computing. It's not like the classical world is standing still at all. And Moore's law keeps happening. The algorithms keep getting better. We keep getting these breakthroughs like generative AI and AlphaFold. So, this is a dumb, naive, provocative question. Are we sure that we need the whole quantum computing universe? The classical seems to be doing amazing things.
I think it comes back to the algorithms that are more efficient using quantum hardware. And we know these algorithms, they exist. We understand them in great detail, the speedups that they can offer. And the incentives of having those available to us are just too good to pass up, regardless of what happens within the classical ecosystem.
Give me a domain or give me an example.
Cryptography, security, right? Absolutely.
The first one that we think about remains.
Yeah,
Okay.
in this domain, this is such an important problem that we have decided as a globe to change every single computer in the entire planet to use new cryptography to protect against this. That is happening right now. 30% of internet traffic is already using post-quantum cryptography to protect us from harvest now, our data being stolen and decrypted later by a quantum computer. So you talk about massive investments in global infrastructure changes that kind of give credence that quantum computing will be a thing. It's something like this, that we're so scared of it that we have to literally change every computer in your pocket, every computer on the internet to protect against it.
Wow.
So I think it is a big deal, and people are so scared of the risks that they're willing to make these investments and changes. So yeah.
Gentlemen?
Well, 22 years ago, Peter Shaw wrote a paper. I think the title was "Why Do We Have So Few Quantum Algorithms?" And if you look at the paper, it's quite old. It's still valid. We don't have that many quantum algorithms. So I think the theory of computation in this quantum world is not developed enough. There's not a kind of global theory of what we could do, what's the real source of the speedups. One of the reasons is we have to learn everything from scratch when you discover that space. You don't develop that.
This is a brand new fundamental.
Totally new. I mean, you think differently. You think about interferences, for example, which is not commonplace when you do a classical algorithm. So you have to think entirely differently. And the other thing that can either bother me or make me optimistic is there are many many paradigms in computing. I believe a lot in analog computing as well, analog quantum computing. I mean, the stuff you do with cold atoms, the stuff you can do even with photons or coherent Ising models are promising to solve optimization problems. So we should bet, like this mess that you described in the US, we should bet on diversity. So there's a diversity of approach. And there's another computing world or realm that is underexplored, it's called unconventional computing. So it's not classical computing, it's not quantum computing, it's in between. And there are many companies there, MEM Computing here in the US. There are many companies exploring various ways of improving the power. And one of the things I'm trying to better understand is what can we do to build those optimization-oriented algorithms, either quantum or classical. There's a very interesting approach that was chosen by a company called Colab, which was created by a team from HPE and former alumni from Google with John Martinis. I know them very well. So what they did was interesting. They said, we're going to focus on quantum chemistry with quantum computing, but we're going to look at photonics, non-quantum computing, to solve optimization problems, and we kind of stick that together. It's very strange, I would say. It's original, but it's very pragmatical. So we have to, since the industry is nascent, we have to be very open in the various technology paths. We have the chance that there's a lot of public money in the academic world, in Europe, in the US, in China. So let's explore all those fields, and it's going to advance science and advance computing, and we'll see the winners, and probably winners with an S, not one winner. There's going to be many winners.
Yeah. Will, we're going to need the quantum world in the future?
Oh, absolutely, absolutely. And I think that we formed the Center for Quantum Engineering here at MIT a few years ago because we recognized that, as many did, certainly weren't the only ones, but quantum is different. And if you want to build quantum systems, that we need a new set of abstractions that are going to allow us to do that. We need to, the rules of thumb. Right? We're not going to apply fundamental physics equations to design big systems, right? And so we need to develop a field of engineering around how to design these quantum systems. And it's a similar story as Olivier was saying with algorithms. What are the algorithmic abstractions? We really don't know that many yet. Quantum Fourier transform, for example. Okay, so this is happening in real time. It's very difficult. Peter Shor is a genius, and part of the genius is that he could abstractly develop an algorithm, right, just from his brain. No fingers on keyboards, from his brain, right? But I think usually for the rest of us, the way that it works is you sit down at a real quantum computer and you type.
Do stuff with it.
And you do stuff with it. Fingers on keyboards. Graduate students, fingers on keyboards is going to help us develop more and more algorithms. Of course, it's bootstrapping. We need a quantum computer to do that. It's got to be performant at a level that allows me to make a better quantum computer. And so this is what's going to unfold, I think, in the next 10 to 20 years. And then, I think that if we are all around, I won't be, but say 2100, and we look back and we would say, yeah, of course, it's obvious that we would move into a quantum, centric world, because the world is quantum mechanical, fundamentally. We're not going to throw away the classical devices. We're going to use them. But that the perspective will be much different. Just as we look back now at what happened in the computing in the 1950s, and we think, wow, that was so primitive, right? What happened in the intervening, 75 years, to us is obvious now, but it wasn't obvious at that time, right? Mm-hmm. And yet, if that development hadn't occurred, if people weren't working on it really hard, thinking they had the computer of the future, I'm going to be the winner at mile 5, I'm in the lead, right? If they didn't do those things, what followed would not have followed.
Yep.
It's very important.
Got it. I want to ask you one follow-up question, sure. And then we're going to throw it open to all of you. So be thinking what you want to ask our panelists. Will, I want you to talk not about the scary part of quantum that's going to reveal all of our secrets and decrypt everything, and this adversary is going to take all of our data, and our mutual fund balances are going to be empty. We can do that, right? Yep. Before we throw it open for questions, give us an example of some things that you think we're going to be able to do with quantum that are profoundly good and hopeful and valuable, that we're not going to get to unless we do quantum. Does that question make sense?
It does, absolutely. I think there's far more good that quantum's going to do than bad.
Yeah.
Mostly because we have post-quantum crypto schemes, we're going to implement them, and then aside from forward security and decrypting things from 30 years ago, it's and that's important, don't get me wrong.
I got it.
But that's not going to form the backbone of commercialization.
Right.
Yeah. Mm-hmm. So I think where quantum computers show obvious promise right now is in scientific computing. And what I mean by that is quantum chemistry, quantum materials, pharma. Big one is pharma, because pharma, 10 years, $1 billion, oops, my drug didn't work.
Yep.
If I could even shave a factor 2 off either of those, huge wins. Boom. Yeah, boom. So
not just for the pharma companies' bottom lines, but for our health?
For our health, that's right, impacts our health. We're worried about climate change. I think it is changing, right? Whatever the cause, it is changing, and we have to do things to either mitigate or fix that change. And that's going to come from what? The climate is an atmosphere, it's chemistry. Materials are how we're going to build things that help us with that. So I view scientific computing of this form as the obvious application, which will have tremendous impact across many fields. That's number one. Number two, and I think this is a real application, although as Olivier said, it's not, it's at best a quadratic improvement, is going to be things like optimization. Everybody's trying to optimize something, right? And we know that, or at least we believe very strongly, there will not be exponential speed up in optimization, right? Okay. I think that the best we can hope for is a quadratic speed up, and it may not even be that. That may be the best it could be.
Oh,
okay. But then I think about some companies that were in our industry membership group, like BMW. They had a scheduling question that was relevant to them of manufacturing, how the cars go in and out, and the people are sick today, and who's on staff, and how long are they working, stuff like that. And they told me that, look, if you can give us 5 to 10% improvement over what we're doing today, that'll save us $50 to $100 million. That's real money.
That adds up, yeah.
It does add up. So, from the academic community, and because we all want the exponential speed up, it's become the mantra that, if it's not exponential, it's not really quantum. Or if it's not quadratic, it's not really quantum. Okay, maybe. But from a practical standpoint, we just want a better computer. Just want to better. And I think there are opportunities there for sure.
I think there's one other thing to add to that, really important, is the quantum impact and connection with AI as well. As AI is evolving, there are algorithms within quantum ecosystem for sampling that can be useful in deep neural networks, or classification for inferencing that we haven't fully explored how they'll come together with that ecosystem yet. And it has to do with hardware maturity or algorithm understanding, but we know they exist. And as they are explored, and there is more of a convergence between what quantum can offer to that ecosystem, as well as how the AI ecosystem is already accelerating quantum development with the way it's accelerating everything else, that will be that is also, I think, something that is a light post for us to look out for.
Got it. All right. Let's hear from some folk in the audience. And please, if all of us could keep in mind that the 3 golden rules of asking a question are that it's short, that it's clear, and that it's a question. Are the rules clear to everybody? Do we have a first brave? Over there. We have a hand up somewhere? Do we have mic runners to bring a microphone to the person? Okay. Sir, could you model fantastic question asking for us following the 3 golden rules?
Yeah, no pressure. I'll keep it short. From the panel's perspective, what is your estimate on Y2Q as a date?
Y2Q.
April.
You define Y2. You define Y2Q for us.
Yeah. It's the next big Y2K. In
April 13, 2037. I have no idea.
Well, if you look at our MIT calculator that we've created for quantum economic advantage, it also gives us some information about that, and you can map out different hardwares and when they would do it. I think the one that we kind of look at is 2032 from one of the IBM machines could potentially be the date, and that lines up neatly with the depreciation of what NIST is saying about the existing cryptographic algorithms that we need to replace. So somewhere in the next 7 to 10 years, maybe.
Yeah, it's a little bit different than Y2K in the sense that we all knew that 1159 in 1999 is going to switch to 2000, and then DOS is going to go nuts. But and it didn't happen.
Yeah, right.
So I think here it's not a specific date, but it's more of a concept that when will we have a quantum computer at a scale that can run Shor's algorithm that can compromise our current public key crypto systems. And we want to make sure that we are well in advance of that, switched over to the new crypto systems that came out and were announced by NIST last year that we believe are immune to attack by future quantum computers. And I think that has been called, to my mind, Y2Q.
Oh, got it.
Yeah, and sure, we need to start switching over right now.
I would replace Y2Q by Y2C. Because if you look at the resource estimates of a Shor algorithm to break a 2048-bit key, it's about the same resources than to do useful chemical simulation. So it's very positive. So yeah. I don't care about Shor. I care about chemistry, like Will was describing. It's the same date. So one way to get an estimate is to ask a specialist. That's what Michel Mosca is doing every year with the Global Risk Institute in Toronto. So they ask, I don't know, the last time was 37 people. And you know what they do? They have a Gaussian curve that's centered around 15 years. And every year, it's always 15 years. So that's all we know. It's a Gaussian curve, so nobody knows. There are so many uncertainties. But when you add all the stacks of the problems to fix, scaling, interconnection, whatever, there are so many problems to fix that nobody can say. I don't think IBM is going to have multiple up to, let's say, 4,000 to 6,000 logical qubits in the next decade. Maybe they plan to have 200 logical qubits by the end of the decade or 2032, something like this. So it's going to be a bit later.
All right, that was a very short, very clear question. Thank you for modeling fantastic behavior for us. We some
over there.
Way in the back. You have a microphone, sir?
Hi. I'd like to ask a question about the public accessibility of quantum. So we talked about press releases, for example, right? So if somebody wants to make a decision about something in any area of tech, they're going to ask an advisor, for example. But the problem here is the advisor is not going to know how to answer the question. There's too much technology in quantum, right? And press releases don't work. I was wondering, do you have resources that you go to resources for somebody who is educated but needs to understand the space? And if there isn't such a resource, I don't know of one, is IDE's, what's it called?
The quantum index report?
Yeah, the conspiracy theory thing about 20% reduction of conspiracy theories. Can we modify that and some chatbot that's going to help us understand what the breakthroughs of quantum currently are?
There are resources available, absolutely. And indeed, that was precisely one reason we formed the Center for Quantum Engineering, and its industry membership group was to help bring members from industry to MIT where they can talk with faculty, students, people who are working in this space. It's also the reason we started the professional development courses, was to really separate reality from hype, introduce the jargon, what does it mean, so that people can become better able to sift through that information that they're getting every day themselves. So I think those are resources that are certainly available today.
I'm going to be very selfish. You got my website, my book.
Yes, your book. I forgot. I wanted to say that. I've been waiting all day.
It's free, so I don't sell the book. But there are many sources available. I mean, you got websites, you got analysts like Bob Sutter and GQI. There are many.
And what's your book? What's your book's name?
Oh, my book is Understanding Quantum Technologies. It may be a fake premise to some extent, but it's very hard to understand.
It's a very good book.
But it's a way to look at all the aspects, including a technology that we have not mentioned at all, which is quantum sensing. It's part of the second quantum revolution, which is also potentially bringing some interesting business value in different fields.
Yeah, it's an excellent book. It's 1,500 pages. It's really comprehensive. It's a fantastic book. You can get it from the website or on the archive. Yeah. One other point I wanted to make on that, and it's related to this, is that it's important that you have trusted advisors in the community, whoever they are. Make sure that your information is coming from someone that you trust, and that often means it's not someone who has a vested interest in a particular outcome, right? But is able to step back and say, okay, this is what I think, this is true, this is, from my perspective, untrue.
It's like error correction in multiple sources.
That's right.
Anything to add?
Yeah, there's so much going on in this area. If I look at what we're doing at the Quantum Economic Development Consortium, there's an entire task force of people focused on understanding workforce development, and it's involving 150 different companies, universities, and government agencies that are all trying to get education out to the ecosystem. There's publications of all the different types of activities that are coming out through these consortiums, whether it's the QEDC or the WEF or QUIC in Europe or other ones, where it's the community coming together to try and produce content that is consistent and relevant across many viewpoints. And those are some really good organizations to go to get information. For us internally at Accenture, we have a awareness, conversant, and job ready program where we make sure that people have the information that they need in order to embrace the ecosystem and be good advisors, or know how to defer to someone who has more context to be a neutral party to answer questions as well. And I know there are a lot of other folks who are trying to operate in that manner too. So.
Over there.
Yep. In the back corner, do you have a microphone?
I have the mic over here.
All right. I'm sorry. Hold on, we're getting to you. Please go.
My name is Ben Linville-Engler. I'm the Chief Investment Strategist for the Mass Tech Collaborative, State Economic Development Agency. I really appreciate the global competition discussion. I think there was a statement around European countries should work together. That might imply that states in the United States all collaborate and work together. Can you all speak to the sort of domestic competition that's going on between whether it's Massachusetts, New York, Colorado, Illinois, California, et cetera? Would like to get your thoughts on that, strengths, weaknesses, opportunities.
Sure, yeah. again, I think it comes back to what we were talking about earlier about advantages of the U.S. approach, which is seems somewhat chaotic sometimes. On the one hand, we have a federal level which is funding globally the entire 50 states and territories. At the same time, at the state level, we're competing, like crazy, trying to, advance our own, interests. So, I would say within the United States, Massachusetts, Kendall Square, very strong, of course, thanks to a lot of work that your organization does. Of course, California, Northern California, Southern California. The Chicago area is very strong. DC area, Maryland. North Carolina, surrounding Duke, Research Triangle, very strong. And, New Mexico and Colorado have made a big play, for sure. I think much like it was said that, maybe the EU and EU countries are seeing this as a way to leapfrog technology. I think many of the states in the United States are similarly seeing, hey, we're going to leapfrog. And then just one observation, which is that, so many, not just states, but countries, entities around the world say, hey, we're going to be the next Silicon Valley. I feel like I've heard that mantra too many times, and I've never seen the next Silicon Valley. So let's make the first Quantum Valley. Or let's not even use the word valley, right? But let's think, how do I do that instead of trying to mimic something else? Yeah.
Anything else to add?
The history of the US is interesting. I'm European, so there's a big difference between the history of a digital economy in the US, where there's a lot of concentration in the Silicon Valley. And when you look at the map, I got a map in my book of all the US quantum ecosystem. It's everywhere. And one of the reasons is the inheritance of the Manhattan Project, because the DOE centers were created after Manhattan or during Manhattan Project, so Fermilab, Oak Ridge, and Los Alamos. And there's a kind of result from that 80 years later. That's interesting to see that. So all the states want to be the kings in town. So it's going to be collaboration. I mean, look at some companies who have multiple headquarters. Who is based in, I think Continuum has an office now in New Mexico. IonQ is also in Washington State. So you have multiple states. Even Microsoft or Redmond, but they have this lab in around UCSB and Caltech, like Amazon. So most of the large companies, they have multiple stakes, I would say. Because, the problem is the talent. I mean, you will have always to fight for talent. So you have to be connected to universities where the talent comes from. And so you can't just stick to one location, one state. You have to be in multiple states. Also, there's a reason why, because many universities are more or less specialized. You don't do the same thing at Stanford, Princeton, here at MIT and Harvard. Even Harvard and MIT, it's different things. So.
All right, I think we have time for one final question, and it's yours.
Great, thank you so much. Actually, great to go second mover's advantage. I'd like to expand on the question you started answering. So now there's all these terms out there, like the AI race, the quantum race. There's a national security phrasing of like technological advancements. So on the question of like competition and collaboration, if you were to take it global, what do you think the right countries competing or collaborating on advancing quantum as a technology to fulfill its potential? From a scientific and a business perspective, what do you think the right balance is in terms of competing versus sharing resources to advance faster or expand the scope of what the technology can do?
I have a quote, which is from a Chinese scientist. I forgot his name. It's in my book. And he said, the problem with quantum physics and quantum computing, it's not companies or countries fighting with each other. It's man vs. nature. I like this quote. We fight with the extreme way to control nature. It's like nuclear fusion. So we need collaboration. Of course, the political landscape, like with China and other places, makes it difficult. But you need... what's important in the quantum sphere is you won't have a Steve Jobs, the guy who invents everything. You need many Will Oliver, not just Olivier, not a single one. So you need many scientists from different disciplines working together and on a global basis to find a way to build those systems. It's not going to be a single place. So that's why collaboration is needed, and we've got to cope with the political landscape. But the history of quantum computing is going to last longer than any political situation, I would say.
I would say you have seen export controls be announced in different areas right now that attempt to limit certain movement of quantum systems that I think are not really viable today anyway. So I don't know that actually hinders the ability, at that level for many things to work together. But it is, people are very conscious of this because of the security implications. We all see the value in it, the chemistry, the science, the material science, cleaning up PFAS and making the world a better place. But there is the cynical version that we can't walk away from. And so long as those two conversations have to happen at the same time, it will continue to grow. Especially, it will continue to be challenging and grow. The challenges will grow as the technology improves and people get more and more excited about it.
I would say at the fundamental research level, fundamental science, fundamental engineering, we should be collaborating as much as we can. It's a hard problem. We should solve a lot of those problems. And that's pre-competitive. When it becomes competitive, of course, there's a national security imperative for all of these countries, right? And it's economic security as well as information security. Where that line is drawn, I think needs to be reevaluated literally annually because the field is moving so fast. But minds should be put to that task because we can't just make, say, one set of regulations that are going to apply for the next N years, right? We need to revisit it constantly, and I think we do that in the United States. Yeah.
It's a beautiful note to end on time, actually. Thanks to the panelists. Thank you all for coming out. Enjoy the rest of the day.
Thank you.
We'll take a 15-minute coffee break, and we'll come back.